So we are going to consider the normal distribution. Yesterday we have considered the uh, binomial distribution. So let us start with normal distribution. Yes. So as we have already mentioned, am I audible?
Yes,
Yes,
ma'am.
ma'am.
Okay. So
Yes,
I
ma'am.
have already mentioned that the random variables are of two types. One is your discrete random variable and the other is continuous random variable. So binomial distribution corresponds to discrete random variable, and corresponding to continuous random variable, we can consider a distribution which is known as normal distribution or Gaussian distribution. This is the most important distribution for continuous random variable. In many of the fields, you can find its application. We shall do some problems also. Now, what kind of distribution will be called the normal distribution? If you consider a random variable capital X, then we can say that this random variable capital X will follow normal distribution if the corresponding shape of the distribution curve is a bell-shaped curve. So a continuous random variable capital X having the bell-shaped distribution will be called a normal random variable, and the corresponding curve will be called the normal curve. For each distribution, whether it is a discrete distribution or continuous distribution, we have the parameters, that is mean and variance of the corresponding distribution. So in case of normal distribution, you have already found that for binomial distribution, the mean is denoted by n into p, and the standard deviation is denoted by root over npq. Q is equal to 1 minus p. N is the number of trials and p is the probability of success. So here also, we can find what will be the mean and standard deviation of this normal distribution. In general, for any distribution, we are denoting the mean by mu and the standard deviation by sigma, or in some cases, you can see that the mean is denoted by m from the name mean, so small m, and standard deviation is denoted by small s also. Now, what will be the density function or continuous probability distribution function? The function, since you are considering the normal distribution, so it will be denoted by n. The random variable assume the value x, and the corresponding parameters will be mu and sigma. And this function, density function for normal distribution, is given by 1 by root over 2 pi into sigma e to the power minus of x minus mu whole square by 2 sigma square. And x varies for normal distribution. X varies from minus to plus infinity. Okay. Now, if you can specify in this density function, you can see other than the random variable x, there are two parameters. One is mu, another is sigma. So if you can specify this mu and sigma, and already you know x assumes the value in between minus to plus infinity. So on after determining mu and sigma, you can specify particularly that normal distribution curve. So normal curve can be clearly and completely determined by specifying the value of mu and sigma. Okay, so there are some properties of this normal curve or normal distribution. What are the properties? The first property is that uh, this, if you consider the normal distribution curve, then this curve will have a maximum at a point which is called mode. You know what is mode? Mean, median, mode. You have done in your statistics.
Yes,
So
ma'am.
what is the
Yes, ma'am.
mode?
Yes,
Yes,
ma'am.
ma'am.
Ma'am,
Yes,
that's
Mode,
ma'am.
particular
And the value
observation of
addition function
highest
assumes
number of
maximum value.
maximum value. Okay. So here, in case of normal distribution, the mode will occur at the point x is equal to mu. Mu represent the mean. So the mode will also occur for normal distribution. The mode will also occur at the point x is equal to mu, that is the mean. So it is the point on the horizontal axis where the curve will have a maximum. Okay. So this is called mode. This is the first property of normal distribution. Then the second property is the normal curve is symmetrical with respect to a vertical axis which is passing through mu, x is equal to mu. If you draw a vertical axis through x is equal to mu, then with respect to this vertical axis, the normal curve will be symmetrical. Okay, so this is your second point. What will be the third point? Third point is, this one I just want to show you. Third point is this normal curve will have 2 points of inflection. You know what is point of inflection? In your first semester course, I think you have done point of inflection, concavity, convexity, and point of
Yes,
inflection.
ma'am.
So what is the point of inflection? Any one of you?
At that point,
Ma'am, where either maxima or minima
Little bit clear.
equal to 0.
Where?
Derivative equal to 0.
The curve
Where?
changes.
Which one will be 0?
The double derivative.
All these are in mathematical concept. I just want to know physically what does it mean. Somebody was telling changes.
Ma'am, when a
Concavity to convexity.
the curve
Absolutely.
Yes,
Changing
ma'am, the
from
curve is
convexity to concavity or concavity to convexity, isn't it? It is a point where the curve is changing its pattern, its nature. It changes from concavity to convexity or convexity to concavity. That particular point will be called point of inflection, physical, from the physical point of view. And those which you are telling, those are mathematical concept. I'm not going to that mathematical concept because those are known to you. So if you consider a normal curve which is symmetrical with respect to, 1 minute, with respect to your vertical axis passing through the point x is equal to mu, then you can find the third point. You can see the third point. This is your third point. The curve has its points of inflection at x is equal to mu plus minus sigma. So if I can show, roughly I am showing that this is your horizontal axis, x-axis, and suppose this is your x is equal to mu, and at this point we have drawn a vertical axis, then a curve of this pattern will be called a normal curve. Now look at this. This curve is, if I say this point is your sigma type, this is your mu, and this is your plus sigma minus sigma. At this point, the x coordinate is minus sigma. Sigma actually is the variance, standard deviation of the normal curve. Now, at this point, probably at this point, the curve is changing its pattern from, what is this part? This part, is it concave or convex?
concave, ma'am.
Concave. Okay. So at this point, this curve is changing from concavity to convexity. Convex curve will be something like that. So this is probably the point where the curve is changing its pattern, and similarly on the other side, this may be the point where the curve is changing its pattern from concavity to convexity. So the part in between mu plus minus sigma, this point is mu plus sigma, this point, A point, and this point will be said mu minus sigma. Okay, so these 2 points, at these 2 points, the curve, normal curve has 2 points of inflection. Okay, one point A is mu plus sigma and the point B is mu minus sigma at these 2 points. And in between mu minus sigma to mu plus sigma, the curve is concave downward, whereas other than this range, outside this range, the curve is concave upward. So this is your concave upward type, not exactly concave, but it is pattern is changing. Because there is another property of normal distribution that the two ends of the normal curve will approach to the horizontal axis asymptotically. So it is not exactly that it is going upward, but it will gradually move, which will be parallel, almost parallel to horizontal axis, but not touching. It is asymptotically approaching to horizontal axis, but not touching the x-axis, isn't it? So this is how we are defining the point of inflection for normal curve, and there are 2 points of inflection. And the fourth property is the normal curve approaches the horizontal axis. Yes, this is the property. Axis asymptotically as we proceed in either direction away from the mean. And finally, the total area under this curve. If you consider this curve, though you can say it is extended infinitely, so we have to restrict ourselves somewhere where the distance between the curve, tail of the curve and x-axis is very, very small. So usually the range for the horizontal range for normal curve will be taken in a finite form. I will discuss that one. So this area, shaded area, the area under the normal curve, any normal curve, whatever be the value of mu and sigma, the area under the normal curve will be always equal to 1. Remember this point. So these are the 5 characteristics of normal curve. 1, 2, 3, 4, 5. Okay. Now, for this normal curve, we can find the mean and variance of the normal curve. How do we find the mean and variance? So, you know that in general, mean of a distribution or mean of a random variable, if you consider the normal random variable capital X, the mean or expected value of that variable, that is expectation of X, that will give you the mean, and that will be equal to what? For discrete case, what is expected value of X?
Summation of x into
Summation
p of x.
Fx. Summation of x into fx. So this is not discrete. This is your continuous random variable. So what will be the expected value of x in this case?
dx into y, ma. Or we should break it into intervals. And
Once again, repeat, please. Yes, yes, repeat.
we had to break it and then integrate, like dx, small
That
interval.
means integration. Integration of x into fx dx within the range x varies from minus to plus infinity. So we can say
expectation of x, the area under the curve.
Expectation of x, mean value. This will be what?
Yes.
For discrete case, you have told summation of x into fx.
Here it will be integration.
It will be simply integration, yes. So integration of x into fx dx, and the range of x will be from minus to plus infinity unless and otherwise it is specified. Okay. In general, it will be minus to plus infinity. Now, we want to find in general what will be the mean and standard deviation of this normal curve. So first we can find the mean, and then the variance can be understood by you also. So by definition, expected value of x, that will be equal to minus to plus infinity x into fx dx. And for normal distribution, your fx means nx mu sigma, and which is given by 1 by root over 2 pi sigma e to the power minus of x minus mu whole square by 2 sigma squared dx. So this is the standard form. Now we have to evaluate actually this one. So I can take 1 by root over 2 pi sigma outside, it is a constant. So it will be x into e to the power minus x minus mu whole square by 2 sigma squared dx. Now I can put a substitution, make a substitution. What? Let us take x minus mu by sigma, because this part is x minus mu by sigma whole square. So if I put x minus mu by sigma is equal to say z, then this exponential part becomes e to the power minus z square by 2. Do you agree with that? I am substituting x minus mu by sigma is equal to z. Then
Yes,
what
ma'am.
will be your
Yes, ma'am.
exponential part? It will be e to
Z
the
square
power
minus
minus
Z square by
z
2.
square by 2. Absolutely. Now what will be dx? Your substitution is
D
x
sigma.
minus
dz
mu
will
by
be
sigma is equal to dx, z. So dx will
Sigma
be
dz.
sigma
Sigma
dz. Absolutely. So it will be sigma dz, and that sigma and this outside sigma will cancel with each other. So you will get 1 by root over 2 pi or whatever it is. We have taken this substitution, and you will get e to the power minus z square by 2. This sigma will cancel with outside sigma, and x will be replaced in terms of z as mu plus sigma z. Now, this is your what kind of integration? This is your improper integral, because the limits are not finite, minus to plus infinity, infinite. So if the limits are infinite, we say that this is an improper integral. So since we are dealing with improper integral, actually we need to show the limits in terms of this form. Limiting value of integration a to b, where a approaches to minus infinity, b approaches to plus infinity. Hopefully you have done improper integral.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
So there you have considered this type of integration. There are three types of improper integral. One is your lower limit can be two, improper integral of first kind and improper integral of second kind. One kind is that where the limits are not finite, and the other kind is where the integrand is not finite. Okay. So these are the two types of improper integral. So here it is an improper integral. Probably this is called improper integral of first kind, where the limits are not finite. Okay. So that type of integral is called improper integral of first kind. Hopefully, I cannot recall just now which one is the first kind and which one is the second kind. Anyway, it is an improper integral, and you know how to write this improper integral. The standard form of writing improper integral where the limits are not finite will be like this. Limiting value, limit of integration of a to b, where a approaches to minus infinity, this is the lower limit, and b approaches to plus infinity. We should write in this manner, though in many cases we are ignoring this directly, we are solving that, and also we are also giving the full marks, but the standard form should be like this. Otherwise, you cannot evaluate this. That's why we should write this. But I have considered this improper integral in the first case, but later on, I have also omitted that. Anyway, in this case, I have shown that. Okay, so you can now evaluate this one by breaking them as a sum of two integrals. One integral will involve mu into e to the power this. Another integral will involve sigma z into e to the power of this. These are the two integrals we have written, and limit a approaches to plus infinity, b approaches to minus, a approaches to minus infinity. There should be minus. Okay, it is not given here. A should approach to minus infinity and b will approach to plus infinity. Now, how can we evaluate this one? Now, let us first consider the first part of this integration. You can see that I think I can do this one anyway. So in this first integral, let us consider the first integral. I am considering first integral, ignoring the limit now. Let me first evaluate this. So it will be mu by root over 2 pi. This is given. I am considering only the first integral a, b, and limit is there already. E to the power minus z square by 2 dz. This is your first integral, and that will be equal to, I'm keeping mu outside, and I'm taking root over 2 pi within integration sign. It is immaterial whether you are taking inside or outside 2 pi. And I'm writing this one multiplied by 1, and then so that it will not change the value. E to the power minus of, I'm writing this z square by 2 in the fashion z minus 0 whole square by 2 into 1 square, and then dz. So that your integration will remain unchanged. Is it all right? Can I write in this fashion?
Yes, ma'am.
Okay.
Yes, ma'am.
Now, yes. Now look at this one. Instead of a and b, let me write minus infinity to plus infinity. Just for simplicity, I'm writing this. This is your minus to plus infinity. Now, what is your normal distribution, normal density function? As we have defined, normal density function is given by 1 by root over 2 pi sigma e to the power minus of x minus mu whole square by 2 sigma square. look at this density function. If I put mu is equal to 0 and sigma is equal to 1, and instead of x, I am using z, then what will be the reduced form? I have substituted mu is equal to 0, sigma is equal to 1. Then what will be the reduced form? And x is equal to z. What
Ma'am,
will
it
you
will
get?
be e to the power minus
To the
z
power
square by
minus
2.
minus x square by root 2 pi.
E to the power minus z square by 2. So that
Yeah.
is also here, which I have written just now. I'm showing this. You can see that in this case also, in this integration, 1 by root over 2 pi e to the power minus of z minus 0 whole square by 2 into 1 square dz. So this integrand, this part, I'm telling this integrand part, this is nothing but a particular type of normal density function whose mean can be said as mu is equal to 0 and whose standard deviation can be taken as sigma is equal to 1. Do you agree with that?
Yes, ma'am.
So
Yes,
I
ma'am.
can
Yes,
say
ma'am.
this is
Yes, ma'am.
So I can say that this is also a normal curve, normal density function with particular mean 0 and particular standard deviation 1. So such type of density function is called standard normal density function. And corresponding curve will be called standard normal curve, and that variable z, where z is equal to x minus mu by sigma. You have substituted here z is equal to x minus mu by sigma. You can see here. So this z variable is called standard normal variate. Standard normal variate, and corresponding curve will be called standard normal curve. So because we are considering the continuous density function, so its integration in the entire range from minus to plus infinity will be equal to always 1, because summation of fx for discrete distribution is equal to 1. This is the property of distribution function. And integration of fx dx will also be equal to 1. Those are the general property of distribution function which we have considered in the very second lecture or like that. So here you are considering integration of a particular continuous density function. So it is of the form integration of minus to plus infinity fz dz type. And this value will be equal to always 1. So even if you consider in terms of x, whose mean is mu and standard deviation is sigma, integration of that normal distribution nx mu sigma will dx, that will be equal to 1, and integration of nz 0 1 dz is also equal to 1. These two are equivalent actually. Integration of nx mu sigma dx within the range minus to plus infinity is same as integration nz 0 1 dz within the integration minus to plus infinity. Okay. So anyway, why I have shown this one, because you can see that in this integration, if you consider the first part, this first part can be written as I have shown here. You can see that this can be written in this form and this value will be equal to 1. So outside only you are having mu. So it is mu into 1. Am I all right? For the first part of this integration, this one, the first integral. So it gives you the value mu.
Yes, ma'am.
Is it all right?
Yes, ma'am. Yes.
Yes, ma'am.
Now we shall consider the second integral. In the second integral, let us first consider just the integration z e to the power minus z square 2 dz. Integration of z e to the power minus z square by 2 dz. We want to evaluate this. I have done it probably separately. Yes, you can see this one. This is your z e to the power minus z square by 2. What we have done, if you put, let in this integration, let z square is equal to say t. So twice z dz will be equal to dt, and therefore z dz will be equal to dt by 2. And what will be the limit for t? I'm not considering the limit because ultimately I will come back to the original variable z. So just without considering any limit, let me first evaluate this one. So if I put t, z square is equal to t, then this integration becomes integration z into dz will be replaced by dt by 2. So I am writing dt by 2 will be there, and e to the power minus z square by 2 will be equal to e to the power minus t by 2 divided by 2. Do you agree with that?
Yes, ma'am.
Yes, ma'am.
Okay. Now you can very easily integrate this. So half is outside. What will be the integration of e to the power t by 2? It will be whatever it is.
Minus
Oh,
2 e
oh,
power minus 3 by 2.
this will be e to the power minus t by 2 divided by half. Isn't it? Whatever be the limit.
Minus
So
half.
this, yeah,
Minus.
minus half. Right, minus half. So this half will cancel. So you are left with minus e to the power minus t by 2, and your t means z square. So minus e to the power minus z square by 2, and that is written here. You can find that integration of z e to the power minus z square by 2 dz will be always minus e to the power minus z square by 2. Okay. So using this relation, now you can find the second integral. In the second integral, it is your sigma by root over 2 pi is constant outside. Integration z e to the power minus z square by 2 dz. If you evaluate it, you will get minus of e to the power minus z square by 2. Now put the limits from minus infinity to plus infinity. So if you put the limits, if you put minus infinity, what will be the value of this? When z is minus infinity, so minus infinity whole square is plus infinity. But its index is e to the power minus. So this will come in the denominator, 1 by e to the power infinity, actually. And that means 1 by infinity, that will be 0. And similar will be the situation for plus infinity. So for both the cases, the value is 0. So the second integral has actually no contribution at all. Okay. So this is how we are getting that the first integral will give you mu and the second integral will give you 0. So ultimately expected value of x, that will be equal to simply mu plus 0, and that is equal to mu. Am I clear?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
This
Yes,
is
ma'am.
how we are getting the mean of normal distribution. So mean of normal distribution will be equal to mu. Okay. Now, in a similar manner, you can also find what will be the variance of normal distribution. Now, how can you represent the variance in terms of expectation? Once you have determined the mean, how can you find the variance?
Ma'am,
Have you remembered?
sigma square minus mu square is equals to, again we'll
Yes.
integrate, ma'am. Integrate of f of x into
Integration
dy.
of what? Yes, once again repeat.
We'll take
It will be
sigma
x
square
minus
minus
mu
mu
square
square
f
is
of x.
equals to integrand of
What is the integrand?
yeah, x square into f of x, ma'am. F of
No,
x
ma'am,
whole
it
square
should
into
be x minus
dx.
mu square f of x.
Absolutely. X minus mu whole square into fx dx. Integrand. X minus mu whole square into fx dx. Expected value in terms of expectation, you have done possibly this one. Variance is denoted by expected value of x minus mu whole square. And that's why when you are taking the integration, it will be x minus mu whole square into fx dx. And for normal distribution, the density function is given, fx is given by 1 by root over 2 pi sigma e to the power minus of x minus mu whole square by 2 sigma square. This is your density function. And again, if you want to evaluate this one, put x minus mu by sigma is equal to z, so that dx will be sigma dz, and you can little bit simplify this in this fashion, sigma square z square, etc. And then you are getting this much. Sigma square can be taken outside, and I can write, consider this one. After taking sigma square outside, I can write this part, the integrand, as z square can be written as z into z. And then it is multiplied by e to the power minus z square by 2. Okay, so this is our integrand, and we shall consider integration by parts. We have taken sigma square by root over 2 pi outside. It is a constant. So first function is z. Second function is z e to the power minus z square by 2. And just now we have shown what is the value of integration z e to the power minus z square by 2 in this case. z e to the power minus z square by 2 is obtained as minus of e to the power minus z square by 2. So I will use that result only, and that's why I have taken the second function as z e to the power minus z square by 2, because its integration is known to us. Okay, now if you want to evaluate this one, then first function into integral of the second. Integral of the second is minus is taken outside. Second is e to the power minus z square by 2. So this is first function integral of the second minus minus this constant is there, minus integral of this integration of differential coefficient of first will be 1, integral of the second will be minus of e to the power minus z square by 2. So this minus and outside minus will give you plus, and it becomes e to the power minus z square by 2, integration of a to b e to the power minus z square by 2 dz. Okay. So again, I can write the second integral. Let us first consider the second integral. I can write second integral as sigma square, then limit of this, or if you want to remove the limit, I can write sigma square. This can be written as this part, the second integration part. This can be written as, this will be equal to, I can write sigma square is outside, integration minus to plus infinity 1 by root over 2 pi and into 1 and e to the power minus of z minus 0 whole square by 2 into 1 square dz. So again, it is in standard normal density function, and its value integration will be equal to 1, isn't it? So contribution of this integral will be 1. So it will be sigma square into 1. I can write sigma square into 1. So from the second part, you are getting only sigma square. Is it all right?
Yes, ma'am.
Yes, ma'am.
Okay. Now consider the first part. If you put the limits, what will happen? Can you tell me what will happen if you put the upper limit and minus the lower limit? If you put the upper limit, what will happen to this part, this function? B means B approaches to plus infinity. So you, instead of B and A, if you think about plus infinity and minus infinity, let us consider the upper limit. Then it will be, your function will be z by e to the power z square by 2, because it is minus. So you can take it in the numerator, denominator. So z by e to the power z square by 2. And now if you put the limit, it will be of the form infinity by infinity type. E to the power infinity means infinity. And z approaches to infinity means it is of the form infinity by infinity time. And same will happen for the lower limit also. Okay. So infinity by infinity type, how will you evaluate that? Using
LHospital
rule.
Or
So you have
else
to,
we can just tell that e per z square by 2 increases more rapidly than z now.
yes, that is the geometrically you are telling, correct. Okay. So using L'Hospital's rule, we can show mathematically that this value has value 0. Okay. So no contribution from the first part, only contribution is that sigma square. So you have obtained that variance is equal to sigma square in this case for normal distribution, and hence the standard deviation will be sigma. This is how we are getting the mean and variance of normal distribution. Okay, any queries up to this?
Ma'am, please explain how the integrand of the variance is coming.
Which one?
The integrand of
Huh.
the variance. How it
First
is
one or
coming.
second one?
Ma'am, the
What you are
integrand
telling?
of the variance.
Variance is equal to this one. You are asking this one?
Yes, ma'am.
So you have done in your statistics. This is just by the definition of variance. Variance of a random variable capital X can be always defined in the form expected value, because from the definition of variance, you know, it gives the variation about its mean value, some standard mean value. So we are taking all, in most of the cases, you may take this mean as mode or median also, but the usual practice is we are taking the variation of the random variable about its mean, and that is given by x minus mu. So just to avoid the sign, we are taking x minus mu whole square. So variance can be represented as expected value of x minus mu whole square. And from the definition of expectation, this is exactly equal to integration x minus mu whole square into its corresponding distribution function. Just from the definition, we have written this. Can you
Okay.
recall this?
Yes, ma'am. Okay.
Okay, okay. Now, 1 minute. I just want to share another one. Uh, 1 minute. Can you see the slide now?
Yes, ma'am.
Yes, ma'am.
Okay. Now let us consider, as I am always mentioning in the property also, I have mentioned that the normal distribution curve, actually probability means for continuous random variable, the probability distribution means you are stating a certain area under the specified curve. So whenever you are considering a continuous probability distribution, the curve corresponding to this continuous probability distribution is constructed in such a way that that will represent certain area bounded by that particular curve and also bounded by two specified ordinate. In this case, the two specified ordinates are taken as, say, x is equal to x1 and x is equal to x2, and above the horizontal axis. That area will be called actually the probability. That means if your random variable, continuous random variable capital X, assume the value, say, assuming the values from x is equal to x1 to x is equal to x2, then according to normal distribution curve, the normal density function is given by nx mu sigma. Then this probability that the normal random variable capital X is assuming the value between x1 and x2, this probability will be exactly equal to the area under that normal curve bounded by these two ordinates x1 and x2. Because you know area is always represented by integration. Integration of what? Integration of that curve which is bounded by some ordinates. So in this case, your curve is nx mu sigma and it is bounded by x is equal to x1 and x is equal to x2. So probability always represented for continuous random variable, probability always represents certain area. And for normal distribution curve, it will be density function is given by this. So that will be shown. If you want to show geometrically, I can show that. You can see that the curve, if you consider this is the normal curve and x1 and x2 are certain specified ordinates, then the probability that capital X will assume the values in between x1 and x2, it will be exactly same as the shaded area bounded by this normal curve, part of the normal curve, and the two ordinates x1 and x2. Geometrically, we can show the probability as an area like this. So you can, if your x1 and x2 are specified, still you can get for two different normal curve, I can show that though the ordinates are same, but still you will get different area if you consider two different normal curve. Both of them are bounded by the same two ordinates. But if the normal curves are different, you will get different area and hence different probability. Why this difference is there? You are taking the area under bounded by the same ordinates, but because you are taking the different normal curve means though
The
the
function
bounds are same
changes.
x1, x2, but your mu and sigma can change. For one normal curve, it may be mu1 sigma 1, and the other normal curve, it may be mu2 sigma 2. And accordingly, you will get different type of curves, and hence that is why your area will be different. Say, I think I have shown, yeah, I have shown this one. Let us consider this figure. In this case, I have considered two normal curve. One is your curve 1 denoted by 1 and the other is your curve 2. Both of them are normal curve. And remember that I have shown that both of them are bounded by same ordinates x1 and x2. Now, if you consider the first normal curve, then you can see the area bounded by this first normal curve and the two ordinates x1 and x2 will be the darker shaded region. Isn't it? The darker shaded region gives the area under the first normal curve, while the cylindrical type of area represent the area under the second normal curve, and these two areas are different though they are bounded by the same ordinates x is equal to x1 and x is equal to x2. This is because what? Because of their difference in mean, because in the first case the mean is mu1, in the second case the mean is mu2, and also difference in their standard deviation sigma. You can see that the pickedness of the first curve is less than the pickedness of the second curve, and also the first curve is much more scattered than the second curve. So these are the differences. Scatteredness is specified by sigma. Okay, and this pickedness can be determined by your mean also. So due to the difference in their mean and standard deviation, the areas are different though they are bounded by the same ordinates x1 and x2. This is how we can represent this. Okay. Now, as I have already mentioned, this part I have already mentioned that it is to be noted that all the observations of any normal random variable capital X can be transformed to a new set of observations of a normal variable, normal random variable Z with mean 0 and variance 1, which I have already mentioned. Now, this can be done by means of a transformation. So, in your general normal distribution, if you put Z is equal to x minus mu by sigma, and if you want to find probability that x will lie in between x1 and x2, this probability by definition will be equal to integration x1 to x2 nx mu sigma. And nx mu sigma means 1 by root over 2 pi sigma integration e to the power minus x minus mu whole square by 2 sigma square dx from x1 to x2. Now it should not be from minus infinity to plus infinity because x is lying in between x1 and x2. So if you consider from x1 to x2, and in this, if you put x minus mu by sigma as z, then you will get this integration. 1 by root over 2 pi sigma is outside. This one becomes e to the power minus z square by 2 sigma dz. And if x is equal to x1 as a lower limit, let us suppose that the lower limit for z is say z1. What will be z1? Z1 will be equal to x1 minus mu by sigma. That is your z1. And similarly z2, the upper limit will be when x is equal to x2. What will be z? Z is denoted by z2 and this z2 will be equal to x2 minus mu by sigma. So I am denoting z1 and z2. So this is how I am representing the derived integration, and this can now be written as I am taking 1 by root over 2 pi, this sigma will cancel. So this 1 by root over 2 pi can be taken inside. So I can write the integrand as 1 by root over 2 pi into 1 into e to the power minus of z minus 0 whole square by 2 into 1 square dz. So it is a standard normal density function. And its integration is also equal to 1 because this integration will be equal to whatever be the, I'm not saying, I should not say 1 because we have fixed the limits from x1 to x2. We are not considering from minus to plus infinity. But even then, if you specify the limits, then this integration will be exactly equal to the corresponding equivalent integration for standard normal curve. So we have obtained that integration x1 to x2 nx mu sigma will be same as integration z1 to z2 nz01. Yes, this one z1 to z2 nz01 dz. And this can be written because nx mu sigma can be written. This integration can be written as probability that capital X lie in between x1 to x2. So from this integration, I can write that probability that z lies between z1 to z2. So probability that x lies between x1 to x2, or probability that x1 is less than x is less than x2, is same as probability that z1 is less than z is less than z2. That I want to mean. So this probability will be exactly equivalent to this probability. And in this case, your standard normal variate has a standard density, normal density function with mean 0 and variance 1. Why I have shown this one? Because this is very, very important while you are going to solve the problem. Already I have shared the normal distribution table with you yesterday. So if you want to use the tabular values, every time, whatever be the problem, you have to reduce the problem in terms of the z variable, because the tabular values are given in terms of z variable, not in terms of x variable. So even if the problem is given in terms of x variable, you have to reduce this in z variable, and then you can use the tabular values wherever necessary. Okay, that's why you have to consider the problem in terms of standard normal variate z. And one more point should be noted: in the normal distribution table, whatever I have supplied, you can see that because normal distribution means certain area. So which area we shall consider? If you are given that some z value are given, you want to find the area corresponding to that, always the area will be given to the left of the specified value z, not to the right, to the left of the specified value z. That area should be always considered. So shall I consider one example or shall I stop?
Ma'am, example.
Then I can show only one example so that you can remember that. That's why I want to show one example. Say, this is the problem. Given a standard normal distribution, that means in terms of z it is given. Find the area under the curve that lies, number A, to the right of z is equal to 1.84, not to the left. To the right of z is equal to 1.84. Let me first consider this one. Okay, so the curve is given in terms of standard normal curve, and you have to find the area to the right of z is equal to 1.84. Now suppose, sorry, 1 minute. Yeah. Suppose I am considering this normal curve. This is the normal curve. And because it is given in terms of z, so I am writing in terms of z. And for normal, standard normal, not only the normal, standard normal curve, because in terms of z it is given. And for standard normal curve, we always know that mu will be equal to 0. This one is your 0. Okay, this is 0. And this one is the positive side of z, this one is the negative side of z. Usually in standard normal curve, the z values are starting from, because it will go up to infinity like this. So we have to restrict somewhere. 3.4 minus 3.4 to the, it is extended in the positive side up to plus 3.4. So area under this will be plus 1. Okay. Now, in this case, you have to find the area to the right of z is equal to 1.84. So z is equal to plus 1.84 means it will be to the right of this vertical axis. Mu is equal to 0 here, 0. So to the right of this, say this point is your 1.84. Z is equal to 1.84 is this one. This is the 1.84. So you have to find the area to the right of this ordinate. That means we need to find this shaded area. This shaded area means total area minus area to the left of z is equal to 1.84. Can I write this? Area to the right of 1.84 will be equal to total area minus area to the left of 1.84. Okay. And what is the total area?
1.
1. So
One.
it will be
One,
1 minus area to left of 1.84. Z is equal to 1.84. Okay. Now look at your normal distribution table, which I have already provided. You can see in the normal distribution table on the topmost horizontal row, some values are given 2 decimal places. 2 decimal places, these are given. And on the extreme left vertical column, you can see the values of Z are given up to 1 decimal place. And on the top, the values are given up to 2 decimal place. Those values, horizontal values, are also Z values. Only second decimal place is represented on the topmost horizontal row, and first decimals are given on the left side of the vertical column. So from the table, you just find what is the Z is equal to 1.8. Have you found that? From the normal distribution table, you just see Z is equal to 1.8 from the extreme left vertical column.
Yes, ma'am. It's 0.967.
So 1.8, and then corresponding 4 value will be obtained from your horizontal top row, 0.04. So their intersection will give you some value. And what is that value? What is that value? Some disturbance is there.
And 0.967.
0.967, absolutely. So area to the left of 1.84 is 0.9671 or whatever it is, 0.967. So you can find what will be the area to the right of 1.84. It will be 1 minus 0.9671, and that is 0.0329. So always the area, whatever mentioned in the table, those are area to the left of that. So even if you are asked to find the area to the right, then you have to convert to the left, and then you can find the area to the right. So I think the first part is clear. And what about the, is there any question for the first part?
No.
Do you have any queries regarding the first part?
Ma'am,
Yes, yes.
ma'am, the table contains only the area of the left part.
Absolutely. Area to the left of any ordinate, whatever Z value you want, area of that. There is no area to the right. Whatever be the probabilities are given, that means area. Those are to, you just look at the figure on the top of the table. It is shown in the figure, the shaded region. See the shaded region, and probably it is mentioned also to the left. Just check that one on the top of the table.
Excuse me, ma'am.
Yes, ma'am, it is mentioned.
To the left. So it means all the areas are given to the left. None of the areas are to the right of that.
Excuse me, ma'am.
Yes, yes, be louder.
Ma'am, if we consider the value of Z to be minus 1.84 instead of 1.84,
Absolutely, absolutely.
then we are directly getting the answer, ma'am, from the table.
From the table, you can find that. To the left, if you are, even if you are asked to find the area to the left of plus 1.84, that is also given 0.967. Since it is given to the
Yes, ma'am,
right.
it will be same, because it is symmetrical now, ma'am, so it will be same.
Yes, absolutely.
Left
yes.
or 1.84
From the
right.
symmetry also you can find minus, and that's, yes, I want to mention one more point, right? That in some of the books you can find that they have given those tabular values only for positive Z values. They have not mentioned the negative one. In this table, negative Z values are also given. The provided table shows the negative Z values, but in some books you can find that the tabular value does not involve the negative Z values, only positive Z values. So why they have not provided? Because from the symmetry, you can say what will be the area to the left of that ordinate passing through mu is equal to 0. That's why they have not mentioned. Now the second one is z is equal to minus 1.97 to z is equal to 0.86. So that is quite easy. You can consider, say, from minus, suppose this is your minus 1.97 and suppose this is your plus 1.84, which we have considered. So minus 1.97 is here. You have to find the area between these two ordinates, this darker shaded region you have to find. Okay. That means you have to find the area to the left of 1.84 minus area to the left of minus 1.97. And that will give you the required area. So what will be that area? Can you find that? Corresponding area to the left of 1.84, that is you have already found 0.9671. And what is the area to the left of minus 1.97? How much is the area?
Ma'am, 0.0244.
Yes, ma'am. 0.244.
0.0244. Okay. So this one, sorry, 0.0244. So subtract these two, that will give you the area between those two ordinates. So this is how we are finding the area under the normal curve. Is it all right?
Yes, ma'am.
Have you understood that?
Yes, ma'am.
Yes, ma'am.
Yes.
Okay, then I think I can stop here.
Okay, ma'am.
Okay, thank
Ma'am,
you. Yes, yes.
if we don't have the tabular form, we can generally use the probability formula for normal distribution, right, ma'am?
If once again, repeat.
If we don't have the tabular form for this z
Yes,
values,
then you have to certainly use the normal distribution density function and you have to evaluate the integration, definitely.
okay, ma'am. Okay, ma'am.
That
Thank
is
you, ma'am.
always there. This is in addition. And in many
Okay.
cases, you need to consider the tabular values. It is not always very easy to use the integration formula. That is why the tabular values are also given.
Okay, ma'am. Thank you, ma'am.
Okay, welcome.
Thank you, ma'am.